Okay, we're going to get started now. It's coming up on 12:10. Oh, I like this mic. This is like, ooh. Okay, welcome back, guys. It's week 15. It's like the fourth week of the semester. How's everybody feeling? Good? Good. Do I need to make my rounds? Because I can make my rounds and start asking people if you don't give me the response that I want. Um, Hope everyone's doing well. I'm doing well. Cyprian is here. You know the vibes. We're going to get started now. Welcome to RIT-Sec. Yeah. Announcements. Please join the Discord. Is the check-in up? Signing up. Can you check that real quick before I proceed? Yeah. Guys, if you aren't in the Discord server, I need you to get in the Discord server. I would assume everyone here is, but I don't know if people online aren't. Um, but, yeah. Okay, thank you, Brayden. Okay, like I was saying, please sign in. You guys know the drill. Oh, Devin's here. I wish I could, like, actively pan the camera around the room and just, like, pan to people's faces randomly. That would be hilarious. But yeah, please sign in. Also, please check the calendar. I'm really liking this mic. I sound very like real. Um, yeah. Oh, it is. Check the calendar, please. That's how you know when our events are. We have some stuff coming up. You know the vibes. Also, join the mailing list. We put a lot of work into that. That's how you get updated with everything that's not actually I can't speak. Actively included in the announcements and the presentations. You know the vibes. Okay. I'll stop talking now about that. Okay. I'll be wanting me to put this in here. RIT-Sec socials. So we're going to the hockey game as a cohort. Join us on the 24th to go to the men's game against Air Force. Meet in the club room at 5:45 p.m. the day of. Tickets will be $5. Details on payments will be coming later. In order to go with RIT-Sec, you have to fill out this form by 2/18, which is like next week sometime, right? I think that's what? Next Saturday. Thank you. Yeah. I'll give you time to scan that QR code. Albert is not even here, which is unfortunate, but you know. Oh, we're so back. Okay. Don't say that. Also, okay. Update from Team Contagion. This is, I forgot the actual MHS. I think it's the high school one. And LACTF signups will close on Thursday at 11:59, this upcoming Thursday, I believe. If you have not been added to the Discord server, please DM Mr. Chandy K and or any other Contagion members. Oh, Dr. Chandy, is he a doctor now? I think so. He's traversed the terrain, been overseas. He knows. He knows. Meet the sponsors. Clap it up, please. Okay. Oh, yeah. Oh, yeah. Oh, yeah. Okay, stop. I really wish I could just, like, pan across the room when we do that. That would just be so nice. Or, like, just have, like, not a macro, but it's, like, a hotkey in, like, the Twitch term, so you can, like, hit the button and the camera pans over. Yeah, I want a stream deck. I want a stream deck, one of the little ones I can just hit the button and the camera. That would be so swag. But yeah, follow our social media. Sophia puts a lot of work into that. Some very fire posts. Okay. As you know, last week we did advanced Windows, so naturally we have to do advanced Linux now, and I have my sweet, sweet boy, Michael Vaughan. Michael Antoinette Vaughan. About to present. Everybody, please give this sweet, sweet, supple man a round of applause.
All right, we got the real mics today. Everyone can hear me in the back? We're all chilling? Very nice. All right, so we're talking about advanced Linux this week. Last year, about the same time, I gave the same presentation. So we're going to cover some of the things that you should know, like essential stuff, and also some stuff that we didn't cover in the previous presentations as much. So if you feel like something's missing, it's probably in the last one or in the ones that I left out of the last one from the older ones. We have like 4 or 5 of these on the channel now. They're all very good and worth watching, so check those out. All right, so we're going to do a little agenda today. Basically, we're going to do some recap from the last time I gave this prezo. We're going to talk about cron tabs and services and other ways to have long-running processes. And we're going to cover file systems, the differences between kernel and user space, ELF files, and netfilter, SE Linux, and a few other things. So that's what you can expect. So yeah, last time I gave this presentation, I focused a lot on permissions, on users, networking details, and on PAM, which handles authentication in Linux. So PAM is a really big concept. It's how authentication works. It's about as important as like LSASS and all that stuff on the Windows side. And yeah, I gave this presentation last year where the same hoodie was a little bit happier. Yeah. All right. All right, so let's talk about some permissions. Files and directories have a user that owns them. So there's a user that owns that file or directory. There's also a group that has like specific group permissions. So if you're that group, if you're in that group, you have those permissions on that file or directory. And then there's permissions for everyone else. And those are expressed as octal numbers between 0 and 7. That's about as exciting as it sounds, but it's actually pretty useful if you want to add up the permissions like mentally in your head. So basically the way that that works is that 2 is for read permissions, 4 is for write, I believe I have that right, and then execute is the last one of the 8 or 7. So yeah, and then of course 0 is for like no permissions for any of those. So we're just going to go right from the top and go through our examples here. Who wants to take our example here and translate it to English? Anyone want to go first? I'm thinking Mr. Werner. What do you think? Yeah, what does that mean? It does, dude. Wrap it up. All right, that's the whole presentation, guys. We're done. See you next week.
It means every user has the permission to read, write, or execute the file.
Yep, and also, yeah, any user, anyone in the group, just anyone period from that last number 2 has full permissions on that file. So if you load like NTFS in Linux, it doesn't have support for Unix file permissions, and everything will have this, which means you can delete or execute anything, which is awesome when you download a bunch of malware samples to that, and then they're executable. Wrap it up. Don't ask me how I know that. Yeah, so what about this next one? How about Mr. Mullen over here? What are you thinking, dude?
So 644, the user can read and write. Everybody else can also write, but nobody can execute.
Yeah, I might have gotten read and write mixed up. So maybe I'm wrong. Maybe read is 4 and write is 2.
Everybody can read, user can write, nobody can execute.
Yeah, so you guys are more right than I am. I always try and remember it, and I usually get it wrong. But yeah, that's how it works. 600 just means that the user can read and write that file, and no one else can even see it. So like your SSH private key is usually 600, or should at least be 600. And then you can also have like 200 if you just want to do that. So cool. All right, so the way that Linux manages long-running processes these days, they box them up into services. And basically what a service is it's just a program that you run, and it usually has a little file that starts it automatically for you and like takes the output and the input from it. And that's really all it is. It's the same as like any other program, but it has some additional help to keep it running in the background for you. And these get started from your init system, your cron tabs, or they get executed by like other programs. So you could have a script that loads something else. That's very common. Most things on Linux are just text. So it'll just be some script somewhere that calls something, that calls some other thing. And it's very easy to change, which is fun. So this is what a service file looks like. I pulled this straight from the last presentation. Most boxes use something called systemd. We'll talk about that in a second. And they describe services in this way. So it'll have like a description, and it will say like it needs to be started after this other thing. Like after the network comes up, you can start SSH, which makes sense, right? You need a network before you start your SSH server. It'll also tell you like how you actually start it. So that's the program that it actually runs, SSHD, and it passes this argument tag D. And if you want to reload it, it sends that signal. And we're basically saying this should always be restarted. So if it crashes or something, try and restart it. Yep, it also has like targets too, which are like a whole other concept. But you can read a lot about these in the man pages. And if you just do like man7 systemd.directives or dot whatever really, you should find it. They might be in a different manual page section, but for the most part, everything in systemd is documented on your box. So if you don't want to Google for it or you don't have internet access or something, it's all there. All right, so yeah, like we said, systemd is the thing that manages your processes, and these are called services. And it basically does a whole bunch of things, and it starts and stops them. The main thing that it does is it handles logging. So it stores it in like a binary log format, which is like very controversial, apparently. But it also does like network management and like DNS and all sorts of other things. It handles your logins and like, I don't know, there's tons. It even does time synchronization. So yeah, it does pretty much everything on your box that's essential. So, yep. The other way that you start things is through cron. So this is like more old school, I guess. You have a cron tab and you just give it like a script to run, and then it runs like every couple minutes, or you can have it run like every second day of the month or whatever. They get pretty involved, but the main thing about cron is there's a lot of different ways to implement it. So what they'll have is they'll have like 3 or 4 cron daemons on your system. And if that sounds confusing, it's because it is. There'll be like 3 or 4 of these that you don't even remember about. You can install like 6 more. And it just makes it hard to keep track of. So if you're like blue teaming, which is kind of like what these presentations are all about, usually from the blue team perspective, you're going to want to keep track of these. And if you don't need it, I would just remove it, because most essential system services are going to be running through systemd. Cron is usually for your convenience. So if you have to like run a backup script every day at midnight, or you want to get rid of users that haven't logged in every day, that haven't logged in a year, and you want to run that script every day or every 2 hours or whatever. So it's very particular. If it fails, it will tell you. But for the most part, it's pretty rudimentary outside of that. You can actually write these yourself, and it uses this kind of format where it has like minute, hour, day, month, day of the month, and then day of the week. So there's this website called crontabguru, which will like roughly translate these into English for you. This is like one of the big like ChatGPT example programs, as well as like translating these to English. So it existed long before that, so it works perfectly fine on this website. But what this is saying basically is if you want to run a cron tab at a certain amount of time, you can plug these in here and get a rough estimate of when that will be. So in fact, it's not even a rough estimate, it's just when it will run. So this is saying 4:05 a.m. probably on every second day of the month, which is */2 every month, and then every second day of the week. You can get pretty particular with these. Some cron tab daemons let you do things once a year, and you can say like @annually. It kind of depends on which software you're running, but for the most part, they will all support this kind of syntax where you can really like verbosely do things. Here's another one where you're starting something at like 12:05, I guess, in the morning in August, like every day in August. Yeah, this is another one. You can really do these for whatever. So it's useful. I think if you're running like systems administration tasks, they're still very useful if you want to do something at a very particular time repeatedly. But for the most part, if you're doing this from like a blue team standpoint, it's useful. But if you don't have a need for it, you should probably remove them. So this is what it looks like in practice. You'll have like a cron tab file. If you run like cron tab tac e, you'll probably see something like this. Here at the bottom is a valid cron tab, which is running, well, I guess like every hour or like every day at 1 a.m. And it just removes a bunch of stuff from a directory. You can also call a script from here, or really whatever you want. Anything that you would run from your terminal shell, you can do with a cron tab for the most part. And it has like a, kind of idea. We have another example commented out here, which runs it at like 5 a.m. every week, and it just creates some backups. So this is really useful if you're trying to run something repeatedly. And that's exactly how it looks in the same website. So every minute past hour 1, I guess. Yeah, so file systems. When you create, switching gears a little bit, when you create a hard drive partition and you want to store data on it, generally speaking, you're going to use a file system. Otherwise, it's just going to be one giant block of data that you can't reason about. And so what they do is they separate data into hard drives, into partitions, into files, basically, in directories. So that's all a file system actually is. It runs in the kernel, and you basically have physical or virtual ones. So your physical ones on Linux are like ext4, BetterFS, and some other ones like XFS and ZFS for like OpenBSD and stuff. There's other ones for Windows like NTFS and FAT32 and like tons others. EFI is its own file system, I think, yeah, it is. They also have virtual ones on Linux. These are much more useful a lot of the time to most people. especially if you're doing like competitions. Like for the most part, you're not going to be setting up your own file systems, but you probably should be checking out proc and sys. Proc is a virtual file system, and all that means is that there's no actual files there. When you open a file under there, the kernel actually talks to you directly. So you can take a look at like how many CPU cores you have, or how many connections you have open, or the full file path of some process that you see in your list. So proc is really just the kernel exposing these details about your running system through the file system. So it means that you can read it and write it like everything is a file almost. It's like the standard mantra for Linux. Most things are exposed as files is what that means. So yeah, if you can read that, I'm impressed. You should probably give this presentation. Yeah, so moving on, we can talk a little bit about kernel and user space. This is a classic diagram. It shows up every time we talk about this. Pretty sure it was in the Windows one. It's going to be in the next Linux one. Basically, you have layers of separation in your operating system. And all this means is that, you know, if you're running, let's say, a program on your computer and that program crashes, well, you have a certain layer of separation, which means like if your homework crashes for 201, you won't crash your whole computer, which is cool. If you're writing on Red Team and your program crashes, it still might crash the computer, which is not cool. And so we try and minimize that using separation rings. So right out here is like where we all are in the green field. Your applications, these are like your browsers or your homework or Zoom or really whatever you're accustomed to writing all runs in what's called user space. So it's very fun in there. There's a lot of protections. If you crash something, it's going to be okay for the most part. And then everything below that is through the kernel space. So there'll be like levels of device drivers that you probably haven't written yourself. Well, some people have. Basically those exist in kernel. So when you're talking to it directly, you won't actually have to go through a direct route. You'll talk through the kernel to your drivers. And yeah, for the most part, the kernel itself is what Linux is. It handles talking to all your hardware. It handles setting up your processes. It also has its own networking stack, so it implements like TCP. Like if you ever wondered like, oh, where is TCP implemented? Like where's the code for that? It's in the kernel. It's in the network stack in the kernel. So the kernel is a very big place. There's a lot going on in there. It's one of the largest open source projects in the world. It's pretty wild. It's like 21 million or something lines of code. So yeah, get studying. Okay. But yeah, so when we talk about kernel to user space, or rather user space to kernel conversations, we usually get into what's called system calls. So system calls implement I/O, and they also implement like essential functions of your computer. So if you want to open a file, that'll be a system call. If you want to open a network connection, that will also be a system call. If you want to start a program or reboot the box or create a directory, all these are system calls. And so what happens is your user space program, like you write in like Python or C or whatever, calls some library function, and then it calls the kernel. And so you have this translation basically where you go into kernel space. It executes that part. It does the actual like reading bytes off your disk, you know, if you're doing file I/O or something, or it hooks up to a socket, or it hooks up to something else on, you know, the network or like a flash drive or wherever you're reading from. So you get this standard like interface through to your computer, which is very convenient because it means that if you're writing like a piece of Python code that outputs all the users on the box or something, it doesn't need to know about what a file system is or any of that stuff. And if you want to learn more about these, there's like hundreds of system calls. They're all documented in the man pages. They're also documented online. So there's lots of resources on this, lots of really nice tables. You can see like what numbers correspond to each. So this is a great diagram that kind of explains roughly what's happening. So if you look on like the far left side, it calls it main. This can be any function in your program. So let's say you're doing your 201 assignment and you're trying to read something from a file. So on the left side, you have a call to read. And what that does is it makes a call into something called libc. So we talked about Windows API last week and how that basically doesn't, it makes it so that you don't have to write system calls yourself. It also does like arguments checking and make sure that you're not trying to read somewhere you shouldn't, and generally tries to prevent errors before you get into kernel space. So what happens is basically the same on Linux, where instead of the Windows API, we use something called libc. And that's basically what implements like opening files. It's also what implements printf. So you'll notice that like socket and write and all these other functions you've seen kind of mirror the library functions you might have used if you're writing C code before. Printf is an example where that's not the case. Like there's no printf system call. It's just a libc function, but there is like a write system call that actually does the writing. So all the higher level like nicety stuff is usually in user space, and then like just writing bytes back and forth is done in kernel. And so in this example, we're seeing here libc read basically sets up a bunch of arguments and then makes a system call into the kernel. And the kernel basically says, okay, we got a system call for read, so we're going to jump to something called sysread, which implements sysread. And from here, from this point on, it has to make a decision about where you're reading from. So if you're reading from the network, it's going to call the code it needs to read from a network socket. And if you're reading from the disk, it's going to call the required file system driver for that disk. So if you're reading from one disk, it might be one piece of code. If you're reading from proc, it will be an entirely different piece of code. But it implements what's called an interface. This is the same kind of interface if you've taken like Java. It's that kind of concept. Not exactly the same code, of course, but basically the same idea where they call a function pointer, and it's like whatever kind of thing we're trying to read from, call that thing's read, which is the file op structure right over there. Happy to get into more detail with this offline, but for the most part, that's how it works. And so your computer is doing like hundreds of thousands of these a day, you know, millions, billions, I guess. Whatever you're up to, for the most part, if you're talking to hardware, it's going to be going through system calls. And so if you're thinking about like, what is this program doing? You know, what places does this talk to? What places does this write to? System calls are a really great way to know. You can trace these system calls and actually see what a program that you're running is actually up to, which is very useful for reversing and also for blue teaming. And so one thing that's important with Linux compared to Windows is that it's very terminal driven. It's like the soul of the OS, right? So with Windows, configuring the system is all through the registry. That's like kind of the bread and butter of Windows is this registry that has all these settings. For Linux, it's basically just text files on your hard drive. And so that's kind of like the way that you configure things, the way that you set things up. So being comfortable with the command line takes a little bit of getting used to, right? Like you probably didn't grow up using the command line, it might be new. But once you get over like that first few weeks of like kind of, you know, learning curve, it's much, much, much faster and much easier to do things for the most part. So we can take an example here where we're finding files. This will find files that have something called the SUID bit. I covered this last presentation, so I'm not going to go into too much detail now. But all that means is that it lets you run a user run a program as another user. So if you want to run like changing your password, it'll run as root. But of course, you don't want to like have total root permissions, right? So you have to be very careful with that. You can also, one big thing for blue teaming is searching by content. So if you know that something's changed, or you're looking for like an IP address, or you're trying to find, you know, a URL or something like that, learning how to use grep is a very useful thing. So there's many different flags. I've only shown 2 here where you're recursively searching, but there are so many. So really, I would not just go off of what's here on the slide and try and get comfortable with grep on your own time. There's tons of these, and the more that you use it, if you try and use it like a little bit every day, you'll get really good at it very fast. But it's like muscle memory. You got to kind of use it or lose it. And you can also search for network connections. This is very useful if you want to see like what's listening on your box, what's the process name associated with that. Like, hey, I'm listening on a port, but what process is actually listening on that port? So here we're grepping for something called MPD. But you can imagine this is like SSH or Apache 2, any kind of service that you're familiar with. So those are the main things that you really want to be good at, especially when blue teaming, but there's so many commands out there, and you can pipe these together to get really interesting results. All right, so shifting gears again, back into kernel space. One thing that we talk a lot about is firewalls. Like firewalls are like the basic, you know, fundamental security thing. They get a little bit of flack these days. It's not a, you know, silver bullet, but they are a very interesting piece of technology. They have existed for a long time. You'll certainly want to be using them a lot if you're in a competition scenario, because network level filtering is like one of the best things you can do. If you prevent somebody who's malicious from even talking to your box, that's a lot better than trying to do any kind of detection or whatever. So the way that firewalls are implemented in Linux is through this thing called netfilter. And all this is a series of hooks into the Linux kernel that are executed when a packet comes in through a certain point. So it'll go through a line of basically interfaces, pieces of code. And along the way, it'll hit these hooks, and you can call functions on those packets. And so that's basically what a firewall is. It registers a callback that's like, hey, when you see a packet, call this function. And that function probably makes a decision about like whether or not we should keep this packet based on the IP address or based on how many we've seen today or how many we've seen in the past few seconds or whatever. And so that's basically how all kinds of packet filtering works on Linux. It goes through netfilter. There are other ways to do this that are not related to netfilter, but for the most part, the way that you're supposed to do it is through here. And this is where you get that per packet level accuracy. So you can change packets here as well. In addition to just filtering stuff, you can actually change the traffic you're getting in. You can change the data or the IP address or anything else that you'd like to break. NetFilter is very cool. If you want to do kernel level stuff, you can write kernel code to interface with it directly. For the most part, if you're in a competition scenario, you've probably heard of things like IPtables to manage it. And so all IPtables is a user land like front end that basically sets up a whole bunch of like chains or whatever and a whole bunch of rule tables. And all those end up being our NetFilter hooks that basically say, okay, if you get a packet, check what it is in the IPtables chains or the NFtables list or anything like that. There's a lot of different options, but this is how they all fundamentally work. IPtables is the most common. On basically every Linux box you run into, you'll have it. It's not super amazing, in my opinion, and a lot of other people's opinions, but it does work. You can filter whatever you want in there. There's also NFtables if you're like super cool. You can ask Braden about that. And there's also Firewall D, which is how it works on the Red Hat side of things. You can ask Casey about that. Yeah. All right, so IPtables is the most common, so we'll cover that real quick. When a packet reaches the network stack, it basically performs some kind of action that you predefine. So that's all it says, and those actions are allowing or dropping. You can like also reject the packet, I think, too, where like you sort of send a response. It's like, no, I don't want this. But for the most part, it's better to just drop the packet, and so that's probably what you'll be doing. Like you don't even want to respond to somebody who's bothering you, so that's the idea. And the basic mnemonic, I guess, is you have IPtables rules, which basically define like what happens. And those are in rule chains, like input and output. And then those are in tables. So if it sounds confusing, it's because it kind of is, to be honest. But that's how it works, for better or for worse. So you have different tables. Like there's one that's like the filter table, it's default. There's also like a NAT table, which is where all the network address translation happens. The mangle table is used when you want to change things. So if you want to like change a packet as it comes in for some reason, you can do that. There's actually a lot of reasonable reasons to do that, but you can do that. Sort of specifically, there is a table called security, which I think is kind of misleading, but that is where SE Linux does its packet filtering. That's for like, you know, big boy security, I guess, or whatever, mandatory access control. And usually these rules are not set by you. They're set by somebody who tells you not to do things and set up the system instead to not let you. So here's how this actually works in practice. We'll show you how to drop a port on IPtables. TAC-L basically lists all your current IPtables rules. The very important thing to mention here is that if you run IPtables TAC-L, it will not show you the rules for NFtables or Firewall D or anything else. So this is a very important concept. A lot of people, like if you're not familiar with like the 10 types of firewalls you can use on Linux, that is a big thing. You won't see it like Firewall D rules in IPtables and vice versa. So here's how we actually take a look. You can see here that there's no actual rules here. There's a chain for forwarding packets. If you're like a router, you'll forward packets. But for the most part, if you're just like a regular client box, most of the time you'll just be looking at your input and your output chains, which sound like what they're written as. Input is for packets that come in. Output is for packets that you send out. And so if we want to block traffic heading into port 80, we can add it to our input chain. We're saying we're going to do TCP. You could also do UDP. And the D port is destination port. So like that's if the packet's coming in, the destination port is the one that's listening on your box. If the packet were going out, the destination port would be the port of the server you're talking to, or process in general. And then we also pass TAC-J, which I think stands for job or whatever. And that basically says just what you want to do. When you see a packet that matches this criteria, what do you want to do with it? And we're saying we want to drop that packet. And after that, we can see down here that we're dropping this packet. The source can come from anywhere. You can also specify a specific source address. Like maybe you don't want, maybe I don't want like Kenny connecting to my web server. So I find Kenny's IP address and I just block him. But I would never do that. So, never. All right, so shifting gears one more time, we have the executable and linkable format. So we talked about PE files last week with Windows. PE files are the file format for executables. So when you like double click an exe, that's the format. Kind of like if you double click a PDF, the file format is PDF. Same thing goes for JPEG. File formats just define how your programs should actually read that file. So like for a PDF file, the PDF file format says it should be in this format, and then your PDF reader reads it from that format, hopefully correctly, and then displays it to you without any memory safety issues, hopefully. And all the ELF format tells you, the executable and linkable format, is it tells Linux how to load your exe. So it tells you where to load all the different parts in memory. It will say like, hey, right in this file at like offset 1000, there'll be a block that's like 10,000 bytes long. Put it at this address and set it to executable. So that's really how ELF loading works. ELF is basically the standard for all kinds of exes on Linux and more. You can see it on like lots of game consoles, on your phone probably. BSD uses ELF. For the most part, if people are building like a new operating system, it's probably going to use ELF or some other format that's not PE. But for the most part, most of them use ELF. Mac OS uses something called Mach-O, which is a lot simpler, which is actually a good thing, to be honest, because ELF is kind of complicated. So part of the reason why it is because it splits files into segments and sections. Segments and sections. I don't know if you find that confusing. I personally do. The way that I describe it and the difference between the two is that segments describe how to load the execution. So you can say that segments are useful for execution. That's my mnemonic. And now you know it too. So that's how they work. They basically are kind of what I just said a second ago, where you have like a block and it tells you how to load it into memory. They also have these things called sections. So for the most part, when you're compiling software, I'm not going to get too into the weeds here, but you'll have multiple object files. So these are like little chunks of code, and then you'll link them together. And the reason why they do that is because if you change one little piece of code, you don't want to recompile everything. You'll just compile those modules. And at the end, when you want to get your final executable, you'll link them all together. And sections help you do that. They tell you, hey, this is where this function is located in this binary. The important thing is that segments are not actually, segments are the only thing you need for loading a process. When the Linux kernel like runs ls or something, it will not even look at the sections when it loads it. I mean, you can check out the code yourself. It doesn't even try and read them. It's not actually needed to load the program. Sections are only for linking object files together for the most part. You can also get some more metadata like debug symbols and stuff through sections, but for the most part, segments are the only thing that you really need to actually load a program. Taking those little offsets and like chunks in the file and putting them into memory is really all there is to it. And we also have these things called headers, which describe where all these start and end. Yeah, so sections go into section headers. Section headers describe sections. So segments are described by what kind of header? Quiz time. What do you think? If sections are described by section headers, segments are described by program headers. Of course, guys, you're on the ball. Okay, so they're called program headers. I didn't make that call, but they are called that. And they describe basically all the segments in the program. Important thing here, by the way, is that segments and sections can actually overlap. That's totally legal. It's actually very common. So deal with it, basically. For the most part, it doesn't matter because you'll only see the segments in memory, really. All the sections inside of it, you might not even see. You might see bits and pieces, but for the most part, all the segments that are a loadable type will be in your final process. So when you run ls, it makes an exec-ve system call. An exec-ve says, hey, launch this program for me. And the kernel says, sure. And it reads it off the disk, and it looks at all the loadable segments, and it loads them into memory. Note is for like non-essential metadata. So if you run file on like a binary, and it tells you it has like commit hash something, or like build hash something else, that's where they're stored in the note segment. And you also can do dynamic linking. I'm not going to get into that right now, but for the most part, that's all stored in dynamic sections. And then they also have interpreter sections, which are like the program interpreter path. For example, like there's one actually right over here, and its file size is, I believe, what is that, 19 in hex. And if you actually take like the length of this string, it actually will be 19 plus like 18 plus a null byte. So it's literally just storing the file path of an interpreter. You can change that path on disk, and it will try and look for it, which is very fun. That's all I'm going to say. All right, so moving on. Another big topic in Linux for Linux security is this topic called seccomp. So this is very relevant if you're doing like CTFs. A lot of CTF challenges go into seccomp. It's also very useful if you're developing like network services, especially, or any kind of software on Linux where you want to have a certain amount of security. And the basic idea with seccomp is you can allow processes to give up their permissions. For the most part, if you're writing a piece of C code, it's allowed to open any file or create any socket or do whatever it wants as long as it has permissions from the kernel. Seccomp is basically like releasing those privileges out and saying, okay, I don't need this process to, create sockets. Let's say your homework doesn't, connect to the internet, but your homework might have a security vulnerability. Let's say somebody exploits that security vulnerability. They can now do whatever they want in the context of your homework's process. So you might want to prevent them from creating sockets or opening files or doing anything else. And that's the basic idea with seccomp. You're releasing the privileges and saying, okay, whatever I have right now is what I need. After this point, I won't need to create any sockets or do whatever. So for an example on the right here, this is calling like opening a file and then writing to that file, and we're saying that's cool. We already have a handle to this file, no problem. But then there's a seccomp policy applied. There's only a couple of these that are like hard-coded. The strict mode like restricts like file opening and a whole bunch of other stuff. You can read about it online exactly what that means, but you can set your own seccomp mode and be very specific about it. You can be like, I want this process to do certain kinds of sockets, or I want this process to only have access to like getting the current time, or whatever you want to restrict it to. So it's actually very customizable. This example is very simple. It's just saying we don't want to open any files from that point on. So after line 15 ends and it successfully runs and everything, you will not be able to open a file. And so that's why when this program is actually executed and compiled, it's compiled into an ELF file. And then that ELF file is loaded and executed, and it says, okay, then it makes a system call to turn on seccomp. And after that point, if you try and open files, it just kills the process. So the kernel just says no, and it sends a sig kill to your process, and that's the end of your fun. So if you're thinking about developing secure software and you don't want somebody to exploit a vulnerability, seccomp can be very, very useful because it will prevent that exploit code from doing certain system calls. So it's basically least privilege for processes. So yeah, it's pretty cool. It's actually not that hard to get started with, and it's a big topic in CTFs. So yeah, check it out. The other big security topic in Linux outside of LSMs is SE Linux. So if you've taken like authentication, raise your hand. Keep your hands raised if you are very confident with SE Linux after. Yeah, so pretty much no one, right? SE Linux is pretty tricky, but we've got to get started with what it actually is. So we have these two kinds of access controls. If you reach back into the dark recesses of your mind and recall 140 or 101, depending on how old you are, I'm showing my age here. Mandatory access control and discretionary access control are the two kinds of access control. When we say discretionary, it means at your discretion. So the root user can set the permissions for anything on the box, and it's up to root to decide what those are. Some of them might be automatic for your convenience, but for the most part, they can be set by you. Mandatory access control is a different kind of thing where the system itself decides what's okay. And then even if you have root privileges, you're not allowed to change that without logging into that MAC system. So that's basically the idea with SE Linux. You can actually create things that root is not allowed to do, or anyone's not allowed to do on that system. And it's very, very fine-grained as well. So you can say like the Apache web server can read its own log file. That's pretty normal, right? But maybe the Apache web server shouldn't be able to start child processes and like execute whatever code it wants. That's the idea behind SE Linux. Is it's not meant to protect against vulnerabilities. You can still have vulnerabilities in your code. You can still have remote code execution, but kind of like seccomp, SE Linux is like, okay, if somebody exploits your software, like worst case scenario, what can they do in the context of that process? And SE Linux tries to minimize that as much as possible. And yeah, if you're doing auth, it might break your homework, which happens to everyone, so that's okay. Yeah, so SE Linux has been around for a little while. It's implemented with these things called LSMs, which I'm not going to talk about today because it's just a big topic. And it was originally written by the NSA for their important security needs. So it got merged in like 2006, I think, and it's been around for a while, and still no one knows how it works. So, yep, that's about all I've got. So I want to open the door to questions. Do anybody have any questions about this stuff? I'm happy to answer them. We can take some more time, or we can take less time. It's up to Mr. Kenny.
Please ask this sweet man questions.
Camden?
Yeah, you were talking about system D earlier and how you can use like start, stop, restart, etc. All the services. Is that like the same or different than system CTL?
Yeah, great question. So systemctl is actually how you manage systemd. Yeah, so there's a lot of systemd like command line utilities. That's one of them. It's a big one. And so if you do like systemctl start, that's what you're interfacing with. So yeah, that's basically how it works. There's a couple other ones. There's like a ton of files you can edit to, even more, but that's exactly what it is, yeah. Yeah, great question. So kernel modules are another topic. They've been covered in some of the advanced presentations of the past. And it basically lets you create kernel code. You can execute it with root permissions, unless SE Linux prevents you, which is a very common thing. And basically, you can write kernel code without having to recompile the entire kernel. So you write like a little module, and that module gets put into the kernel, and it does wacky things. Yes, I can. It takes a while to get used to, and I actually gave a talk about ELF stuff like last year, and it was talking about ELF viruses, which was fun. Emmanuel gave a talk even further back about ELF. So if this doesn't make any sense, I definitely recommend anyone to check out that stuff because it's actually kind of complicated sometimes. But the basic idea is that segments describe like which parts of the program actually need to be loaded in at runtime. And they are the load segments over here. So when you run like ls, the Linux kernel will read that file into memory. It will look at the ELF header. It will make sure it's actually an ELF file. If it's a PDF file, it will just fail. Make sure it's ELF, check for the header and all that stuff. Then it looks at the program headers. And that basically says, okay, what do I need to load? Which segments do I need to load into memory? And from those segments, from those headers, it will say, okay, we need to load these at these specific places. So I believe this output is from readelf. It might be from object dump. There's a couple like command line utilities that you can use to see this. But from left to right, this is basically a big struct in C. If you're not familiar with that, that's okay. But that's all it really is. So you have an offset in the file where things are located. So this is saying like right at the start, basically. You have a virtual address. That's where it's loaded in memory. The physical address usually doesn't matter. It's usually the same. And there'll be like a file size. So this is like how much you start reading from here in the file, and you read that many bytes, 5C4, in that first load segment. So it's 5C4 bytes long. And it should be about 5C4 bytes when you actually load it into memory. Sometimes it'll be a little bit different, like in the second example below it. Usually it's for alignment reasons. And additionally, memory pages in Linux have permissions. So there'll be certain pages that you're allowed to execute and certain ones you're not. You'll notice here that this is readable and executable. So when you're looking at an object dump output like this, you can safely assume that this is probably an executable, like the code part of your exe. So if we're thinking like what is in that segment, it's probably machine code that you can read as assembly. So if you're doing like reverse engineering, that's where this important stuff is for the most part. And then the alignment is kind of, it varies, but for the most part, it just needs to be, the virtual address needs to be the same as the file. Yeah, it needs to be the same as the file size needs to be the same as the offset modulo alignment. I don't know if I got that right, but it doesn't actually really matter, to tell you the truth. So it just tells you where it's going to load, and it makes sure that it has enough space, basically. So yeah, memory pages in Linux are like 4 kilobytes. So as you can imagine, you might need to go over that or like just under that. And so sometimes you'll need to allocate more pages than you need. But those pages will always have the same permissions. So even if you're at like the very beginning of a new page, it'll have the same permissions as the rest of the page. So yeah, if you're looking at this and you see a program that has like readable, writable, and executable permissions, that's like also kind of like an alarm bell thing, because like there's usually no reason, like legitimate reason, for a program to load things as read, write, and execute. if you run object dump on that virus that I was talking about a second ago that I wrote, you will see that, and you should be like, that's not normal. So yeah. Yeah, that's a lot. So I would recommend just kind of staring at this for a while. Try and run it on like binls on like your home box, in the demo boxes maybe. A lot of fun. But yeah, great question. There are ways to bypass SC Linux. So the important thing about any piece of software that you're using here is that this is being ran by the operating system. It's not being verified by hardware. This is not like a trusted computing system where like there's some part of hardware that's actually blocking you from changing the software. But theoretically you can, especially if you're not using secure boot, just change SC Linux on disk, add some code to it, maybe disable some checks. Let's say you hypothetically insert a kernel module that disables SC Linux. Just thinking out loud here. Yeah, so SE Linux basically exists in the kernel as a security module, and whenever like files are opened or whenever like network connections are made, it'll go through SE Linux, and SE Linux will decide on whether or not that's allowed. So yeah, it's definitely possible to bypass any of these, especially if you have physical access to like a powered off box and there's no encryption or whatever. Yeah, that's what Vasu did not too long ago. We're so back. All right. We want this back.
This sweet, sweet man. Oh, yeah. This presentation was so good. Everybody give Michael Vaughan a round of applause,
Appreciate
please.
it, guys. Thank you for coming out here. All right, it's midterms. It's going to get busy, so thank you for making it out.
It
Have
is
fun with the demos.
midterms. Oh, my goodness.
Have fun with those demos.
Okay.
I think I put my, we should hit escape here.
Okay. I just want to bring this back up because this is heat. I found this on the internet,
I didn't add
actually.
this into the slides, by the way. This is all-
He wanted to present his capstone project, and this is his capstone project.
That's the next research presentation. Coming next week. Anthony,
Yeah.
Put a spot in for me.
Yeah, I dropped a little link in on like breaking TPM chips in the hardware chat, but people don't use it as anyway, I digress. You saw it? It was swag, wasn't it? Okay, we're gonna move into demo time now. And yeah. Demo time and a little pizza in a little bit, Can I get another round of applause for Michael Vaughan? Because we love Michael Vaughan. All right. Yeah. Okay. Okay. The end. Everybody, you can't wave at stream. Okay.
Yeah, I can't.
You can't wave. Okay.